Hey, welcome folks. I'm going to be appreciative of your time and we'll get started right away. So hopefully we'll finish on time as well. I'm Nathan Jones. It's an honor and a pleasure to be here. My only hope is that I'll pick up one thing that's kind of cool from this talk. That'll be time well spent. So I got this up here because I got presentation materials at that link if you care to follow it, and kind of a sample little repo down there that we're going to go through. Okay, so the talk's called Make Your Own MCU Boards, and the story for this goes back a couple years when in grad school, the summer after my first 2 semesters, I sat down to make a little project and realized that I really only had the skills to do that on the development board that we used in our classes, in the IDE that we were using, and I didn't really know how to start from scratch, right? I kind of had my hand held up to the point where someone said, this all plugs together and works, and I've done that for you, and now we're going to program it. But I was looking at development boards, like the ones we used in class, and I'm sure you've programmed a bunch. This is a random one from the little swap pile over there. All right, this is a little TI board, and I said, well, there's an engineer that put this on this PCB, right? This board. Well, I don't know what this one costs, but if I was going to go buy a Nucleo board or an Arduino, and I wasn't going to buy it from a source that was disreputable, I might still be paying anywhere from $10 to $25 for that development board, right? And I can go on to DigiKey, I can search for microcontrollers. I know they cost as little as 50 cents or $1 or a couple of bucks. So I said, okay, there's got to be. How do I do that? How do I put a microcontroller on a printed circuit board and get it to blink an LED or something? So. I did my best to pick up some skills. I managed, I feel like, to successfully do that a couple of times. You can see one example right there of me playing around with the STM32, and I'm going to share with you just some of the tips I learned. The takeaway, I hope, is that you realize it's not, if you've never done it before, it's not as hard as it seems like it would be at first pass. There's a lot maybe that looks like it's going on here, but to just get a microcontroller on a PCB or on a breadboard is not difficult. Okay, so that's kind of our goal, right? We're gonna hope to take a microcontroller that we want to play around with and put it on a printed circuit board, so we can throw it in a project, or maybe put it on a breadboard. And if we can keep it small and cheap, then all the better. So the first thing I want to make sure everyone knows is that on these development boards that most of us are used to working with, in almost every single case. Part of the reason why they're kind of complex, part of the reason why they're not so cheap, is that in addition to there being a microcontroller on that breadboard, there's also something called a debug adapter. And this is the device that allows us to plug in a USB cable and talk directly to the microcontroller, to not just load program onto it, but also to kind of step through debugging if we're using like the STM32 Cube IDE or something like that. Okay, so we're gonna focus on really just putting the microcontroller on the breadboard. Every manufacturer sells a standalone debug adapter that we can plug into that board. Okay, so step 1 is draw the circuit. Maybe step 0 is figure out which microcontroller you want to play around with. So I showed you on this board right here. I've got a STM32 F302. Okay, so if we pick let's say this one right here, this STM32 F302K6. I want to play around with this one. All right. Let me go to the. Oh, here we go. Here's our documentation. All right. Yeah. So I'm gonna look for 2 things. I'm gonna look for the data sheet. And I'm also going to look for something called a hardware development guide. All right. Here we go. There's the documentation tab. ST, here we go, getting started with this STM32 F3 series hardware development guide. ST provides these separately. A lot of manufacturers provide them separately. Some of the manufacturers will sort of just have a section in their data sheets that talks about hardware development. But in any case, there's something from the manufacturer somewhere that says, hey, if you're an engineer who's trying to build a development board, or you're trying to put our microcontroller in your product, these are the things you need to know about the basic circuit that goes into that device. And let's see if I can show you an example down here. All right, here's a little reference design for that STM32F302. Yeah. And I'm not sure if I'm going to be able to rotate. But hopefully, we can kind of see, this is the whole schematic, right? And the pinouts here are like to a debug adapter. There's like only a handful of components we need. And the manufacturer's saying, this is all we got to do to make sure that we can load code onto this device and get it to run it. So as you dig through this hardware development guide, as you look at the data sheet, you'll realize that there are really only about 3 things that we need to make sure we provide to this microcontroller in order to get it to work. One's power, okay? One's a clock source, and that doesn't necessarily need to be external. And one is some kind of connection to that debug adapter, to that programmer. Believe it or not, just about every microcontroller I've seen requires almost 0 external components to just load code and run it. Even the STM32, really all you need is a regulated power supply, and you can load code and run code on that device. So a lot of the stuff kind of in purple is kind of nice to haves, but it's not even really required. For power, like I said, we just need a regulated supply of some sort. The data sheet will tell us what voltage range we need. Most of some of the complications in the development boards and even in the one that I kind of put together just come from providing options. You want a couple of different ways to power the device. Potentially, you might want to use power to come out of the development board to send power to the rest of your project. So making sure those power supplies don't backfeed each other is kind of the biggest complicating factor here. You can see one kind of example here of kind of the simple way that I might plug multiple things together that don't back power each other, and that's just to insert a little Schottky diode in between that power source and the regulator. So the diode will make sure that if I've got a battery connected and my USB cable, they don't send power into each other. The Schottky is preferred, but it's not required just because it has a really low voltage drop once I'm drawing current over it. So that will go into some type of regulator that I send to the input pin on my microcontroller. And like I said, if I've got a 3.3 volt or a 5 volt power source already available to me, I don't need the regulator. Right? That's just a nice to have. A lot of microcontrollers will have an analog input pin or maybe like a battery backup input pin. So you can see here a couple examples of how you might set that up. It depends a little bit on which microcontroller you're using, but the hardware development guide will give you recommendations on how to connect those together. Right? So that's all we need to provide power to the device. The microcontroller needs a clock source, but that doesn't necessarily need to be an external clock source. Right? Every microcontroller just about has an internal clock, which depending on which manufacturer it is, can be accurate to a couple of %, which is perfectly fine for most applications, including UART and I2C and SPI. And in some microcontrollers, you can actually kind of trim that down. There's a register or two that will allow you to sort of, for a single microcontroller, fine-tune that internal oscillator. It's really only if you're going to do like USB or maybe like really high-speed UART, like in the megabaud range, where you want a more accurate clock source. If you're going to do that, my best recommendation is to find what I think is called an oscillator. Not a crystal oscillator, just an oscillator. And this is a component which you provide power and ground to, and it emits a wonderful little square wave that's super accurate. You can send that typically into one of the clock input pins on the microcontroller, and that can be used as your clock source, either high speed or low speed. You'll see a lot of designs that use an actual crystal or a resonator. And at the risk of belying my ignorance, I'm going to discourage using that. And the reason is just because to get that circuit design right, there's actually a lot of physics and heavy math that goes into making sure that that circuit's been designed correctly. I've built them before. There's a bit of a margin of error, but the problem is that unless you've done the math, unless you've really like characterized that circuit, then you've got no idea whether your crystal is taking a long time to start up or whether it's being overdriven and the results can be not as accurate a clock source as you think you're getting or early degradation of that crystal. You'll see these in designs, but if you want something that's robust, unless you're willing to go through all the calculations, I'd recommend paying a little bit extra to go with the oscillator. And then we need some sort of connection to our programmer, which really is just some lines coming out to a pin header. If you've got the programming pins that you're also trying to use as some form of GPIO in your circuit, then the development guide might tell you to connect some resistors before they go to your what devices you're using them to drive them, so that the programmer doesn't compete with those. You have the option of adding a reset button with a little pull-up resistor, but it's not required. On the STM32s, a lot of them actually have internal pull-up resistors on the reset, so you don't even really need that for the device to operate. And with that little setup, we can start connecting to our programmer and loading and running code. All right. The data sheets and the hardware development guides will also talk about any sort of manufacturing specific things, like what boot pins need to be connected to, or how should we take care of unused pins if we're striving for a low power design. So that hardware development guide is definitely your friendly reference. And then, a lot of boards like to have some sort of power LED, right? Or a built-in LED, just so you can kind of do a proof of life once it's connected. This is an example of something I actually showed just at the last workshop of for PIC microcontroller, how to wire it up for that. So you can see I really just have the one external component here, a little pull-up resistor on my reset pin. And other than that, I'm connecting it to a regulated power supply. I've got a little built-in LED that I'm going to use to blink, and that's all I need to load power or load code onto this device and start running it. All right, so once I've got my circuit together, I need to choose how I'm going to build this thing, and that'll drive what parts I look at, what my layout's going to start to look like. So I can breadboard microcontrollers. I can even breadboard really fast Cortex-M devices like the STM32. I can use proto boards to make a little project, or I can actually make my custom PCB. All right. Don't forget your debug adapter. You got a couple examples up here of the ST-Link version 2 and version 3 that are used to program the STM devices, and MPLAB Snap to program the PIC devices. Remember, we're not putting that on our circuit, so you got to buy that separate. If you're building on a breadboard or on a proto board, then you're kind of restricted to anything through hole, but that also includes any breakout boards. You can see a couple examples down here of breakout boards from Adafruit that you can get for SOIC chips and TS-SOP chips and QFNs. There's a link right there from a company that provides breakout boards for surface mount components in just about every footprint. And not that. If we go to the presentation materials, in here is a little Google Docs with a list of links here to some product pages and some stuff about clock design. And you got a couple other links down here for other manufacturers that provide breakout boards for all kinds of surface mount components. So even though we're using a breadboard or a proto board, we're not strictly restricted to just things that are through hole. If there's a really critical component that we can only find in a surface mount, we can potentially find just a breakout board for it. And that's maybe how you would take a microcontroller that doesn't come in a breadboardable footprint, which almost none of them come in that footprint anymore, and actually still put that on a breadboard or a prototyping board. Additionally, if you're using a proto board, you could get a little creative and potentially, for larger size surface mount components, just solder those directly to the little pads on the circuit board. If you are laying out your own circuit board and you're going to do the assembly yourself, of course, there's no restrictions on what parts you put in your design, just whatever you can assemble. But I'm a fan of JLC PCB assembly for just kind of small hobby stuff. Alvaro gave a great presentation a couple hours ago about how he used that for one of his projects. And I'll talk a little bit more about using that service at the end. If you're going to go that route, then you're just kind of limited to whatever parts are available in JLC's parts library, which at this point is still close to 4 million, of all kinds, through hole and surface mount and a bunch of different things. I've got some examples down here of USB breakout boards that you can include in your design, even if you're breadboarding stuff. And for power options, DC jacks or using the USB for power, here's an example of a breadboardable oscillator. So this is I believe it's an 8 megahertz oscillator that you can still find in a through-hole format. And if you're looking for common parts, this was a kind of a helpful wiki. I think I don't know if it's been updated in forever, but it was a great spot for me to, like, if I'm just looking for a connector or a switch or a button, to go there. There's links to DigiKey and Mauser and I think Jameco on a bunch of commonly needed parts for hobby projects, and that typically would at least send me to the right part of the DigiKey website, so I knew which sort of, where I needed to look to find the part that I needed. All right, and then once we've sort of picked our parts, we know how we're gonna attempt to construct this this MCU board. We got a couple different options for circuit layout. So the columns from above, right? If I'm breadboarding stuff, then I'm kind of restricted to just some pen and paper. But you can find worksheets online that will, like that one, that'll kind of make it a little easier to kind of plan out your circuit. If you are building something in a proto board, you can do that. You can also use a software like fritzing to kind of help you orient and plan parts. And the nice part about that is I can make sure to enter my schematic, and if the schematic is correct, then when I go to this little layout perspective in fritzing, it'll help me make sure that I'm not shorting something and I haven't missed any connections. I could potentially also, although you might need to play around with it, use an actual CAD program. If I just enforce the grid to be, 1/10 of an inch spacing, then I essentially enforce that through-hole layout in my CAD program. And if I arrange my components the way I want it, I can even potentially let the auto router connect everything up, and then I just have to make a sort of mental translation depending on whether I'm using a strip board or a simple proto board, how to take the traces that are on that through-hole format and transfer it to my strip board. I'm not going to go into actually how to do that layout. That's a talk for definitely a different day. I'm not going to squeeze into a half hour how to use Eagle or KiCad or whatever. But I will say one note on our layout here. We might be concerned about a couple of things, which include high frequency stuff. So I'll give you a couple rules of thumb. Right? In terms of highest frequency, if I'm using a breadboard, it's somewhere in the low megahertz range. I've breadboarded with up to like 4 or 5 megahertz, I think, without any ill effect. But definitely if you're over 10 megahertz, right, that's going to be difficult to breadboard with. And if you're doing your own layout, it starts to get complicated real fast. Here's your two rules of thumb from an app note by Sierra Circuits, which is also linked in that references slide. If you're over 50 megahertz, you're definitely in the high-speed realm if you're laying out your circuit. The other way to look at it is to kind of compare what's my max frequency and how does that compare to how long a trace I'm running. The actual definition for a high-speed circuit kind of depends on the rise time of a signal and also how long a wire I'm trying to send that signal down. So it's possible even to like accidentally run into a high-speed circuit at a very low frequency if I have a very fast rise time or a really long cable connector. But if I roughly take this equation here, 6.9 divided by 0.012 times the length, where length is that length of that trace I'm running on my PCB, that's a rough rule of thumb for when I'm in that high-speed realm. I want to give you a couple more notes if I'm laying something out on a printed circuit board that will hopefully help you out. One is that I definitely, at this point, I should be thinking about who I want to manufacture my printed circuit board, and I should be looking at that manufacturer's capabilities to make sure that whatever I lay out is they can actually build for me. JLC PCB has an Eagle rules file that I can use to help make sure my design is within spec. Alvaro was a fan of KiCad. He had a link earlier in his presentation to a similar tool for that piece of software. It's not perfect. I definitely have had designs that passed the rules check that JLCB themselves kicked back and said, hey, we can't produce this, but it's at least a starting point. I can put lots of options into my MCU board, which power supply I want to use and whether I want to include an oscillator or not, by potentially throwing in a couple of 2-pin headers that I can sort of drop a header pin and a jumper on, or I can close that with a trace if I want that to be on the board by default and just sort of cut that with a hobby knife or a Dremel if I want to remove it. I can do the same thing with just like the pads of an 0805 random component. And if I'm assembling it at JLC PCB, I can even sort of choose at assembly time whether or not I want to put like a 0 ohm resistor across that pad to kind of optionally include or exclude something in my circuit. And I can find, of course, test pad signals to include on all my designs. I'm not super great about this, but the rule of thumb I've heard is, one test pad per net, if you can, is good. That way it's easy to scope and probe if there's any problems. And then I've got a link up here to a neat project called Debug Edge. This is a project that tries to use edge-to-edge PCB connectors to make the connections to that programmer, that debug adapter that we're going to use to program our microcontroller. You can see on my board here, I'm using that in the upper right-hand corner, but I also left a footprint for an actual kind of if I want to drop in like a 10-pin connector to try to program my STM32, and that's pretty honking. That's a pretty honking footprint right there. And those parts the headers are at least 50 cents or so, which doesn't sound like a lot, but if I'm trying to make this board for $3, 50 cents is, gosh, that's 16% or so of my total budget. So if I can cut that out, then that's helpful to me. So the neat thing about the Debug Edge is that it's a lot smaller. I can put it all the way close to the edge. It doesn't take up as much space, and there's 0 connector. I have to buy 1 connector for the other board to make that mating, but that's it. So there's some niceties there. Okay, additionally, here's some rules of thumb for what's the kind of the max current, max voltage I can push through this PCB. Most of us are probably not messing around with this at all, but it's helpful at least to know what the upper limits are. For a 10 mil trace on the outside of my PCB, about 3.5 amps is what I can push through that trace. And as long as my closest traces are not closer than 24 mils, which is would be the distance between like 2 header pins, 2 pads at a 1/10 of an inch spacing, then I can have 100 volts DC roughly before they start to arc. So as long as we're well within that, we don't have to worry about it, but there's links in the resource document if you want to see how those are calculated. If you're ever kind of getting close, you want to make sure that your design's not going to spark or melt or something like that. And then when we actually go to construct this microcontroller board, again, I've kind of got the 3 columns. So if I'm breadboarding it, all I got to worry about is soldering stuff to my breakout boards and wiring it up. If I'm using a proto board, I'll use those as well, but I might also use my Dremel to either kind of cut through a trace on my strip board or drill out a pad to kind of break a connection between 2 traces. I might use the hot plate or the toaster oven, super advanced techniques to do some easy surface mount soldering. If you are, like me, still not super comfortable with a really fine tip pen soldering iron. And you can also use some assembly services. Some of these get really expensive really fast, but these are the 2 that I found which were the cheapest and for just kind of, I think, low volume or hobby production work, perfectly suitable. JLC will produce for you a board. I think they'll only do one side, but they will do surface mount or through hole. And you can see the equation kind of here. There's a kind of a base rate of $9.50 to start the assembly process. They'll charge you, 0.17 cents for each of your surface mount pads that are being soldered, right? So if I've got a resistor, that's 2 pads. They'll charge you 1.7 cents plus a flat $3.50 fee if you've got any through-hole components. And then they'll charge you an extra $3 if you're using any extended parts in their library. Their library is separated into basic and extended. Basic are parts that are just sort of live on their giant pick-and-place machine. There's no extra cost using them. But if you pull out some extended parts, that's they sort of have to put on and off the pick-and-place, so there's a nominal extra fee for that. On this board here, I think the button there, the push button that I'm using is a reset button, and you can see a little surface mount oscillator here that's Q1 next to the microcontroller. I think those were like the only extended parts. So this board, depending a little bit on how much you populate, you can get for $3 to $5 in quantities of 10 from JLC PCB. So that was kind of my experiment, and I think it worked well. Maker Fabs is another one that'll do the assembly for you at a relatively decent cost. Their rate is effectively $28 base rate plus 3 cents per SMT pad or 4 cents per each through-hole pad. Excuse me. And let's see. Somewhere in my box up here, I've got some samples that I've done, so you're welcome to come take a look at them afterwards. The repository also kind of walks you through this board here, and shows you the yeah. I wanted it to be very self-sufficient, right? So I put a ton of information on the silk screen on the back for someone that just kind of randomly maybe found this at the swap or something like that. That tells you, hey, what's the max voltage that you can put into this thing? Apply to VDD. What's the max current that you can pull out of the GPIO based on the MCU. One of the things I thought was kind of cool about this board was I actually designed it to hold the STM32F103, which is the microcontroller that sits on the blue pill. Of course, that wasn't available a year or so ago when I finally put this together and went to go order it. So I started looking, okay, what other microcontrollers might have the same footprint? GigaDevice is one company that seems to be a bit of a knockoff of ST. They had a bunch of microcontrollers that seem to fit. ST themselves, it seems like, has done a good job of trying to kind of match footprints as best they can. So let's see, I think I found about 125 microcontrollers that all, in various forms, fit this footprint here. So that was kind of one thing that was cool about this project. And then I've got further down in here, you know, how to order it, how much it might cost in different configurations if you have the oscillator, if you don't have the oscillator, if you include a power regulator, if you don't. And I talk a little bit about the schematic. For that board here, this is that schematic. And you can see that, you know, I got my microcontroller over here going to a bunch of header pins. Here's my little power circuit, right? It was, like I said, the biggest reason that there's so much stuff there is just because I wanted a lot of options. I figured I might want to provide power from the debug adapter. I might have a battery attached. I might want to provide power out to some other part of my circuit. So that ends up being the most complicated piece. The STM32 has a couple of boot pins that control whether or not you're booting into like the direct firmware update or into user code or into somewhere else. So there's some pins there. And I have my little oscillators, but that's about it. So if you poke around the repository, you can kind of see that explained here and what can get attached to which pin and how you can use the thing. So hopefully you picked up something new. The hardware development guide, right, is your friend, and it's not as hard as it seems. You can start as simple as this, right? Adafruit has QFN breakouts and QFP breakouts. So you can find microcontrollers that are in those footprints that are in the SOIC or the T-stop footprint. Bake them in a toaster oven and throw it on a breadboard and start building those circuits. Hopefully that repository and that reference sheet provide a lot of useful information. But that's all I have. I'll take any questions now. And thanks for your attention. There was one over here that I skipped over. A question.
Just the information that was printed in the subscreen on the back of your carrier board. Did you refine that throughout the process, or was it one and done and it's sufficient? How from student feedback maybe refine it?
Oh, you know, great question. I don't know if I've got any specific feedback about this silkscreen. Definitely in the process of putting the board together before I sent it out for assembly, I refined that multiple times to try to find a way to crunch the information down, but still make it readable. Yeah. Thanks. Anything else? Okay, well, if you want to care to stick around for a minute, I'll set out those sample boards up here if you want to take a look at them. Otherwise, enjoy the rest of the conference, folks. Thanks for everything.